This video serves as a follow-up to the first video I had on differential equations, which went over how to solve a differential equation. And in this video, what we'll take a look at is the concept of a slope field, which is a visual representation of a function based on its derivative. And the goal by the end of this video is to leave you feeling comfortable with the task of generating a slope field. So we're going to reach our goal by considering the following problem. Generate a slope field given the differential equation dy over dx equals negative x over y using the points shown on the coordinate grid. And the big idea for this is to consider what this represents. And I mentioned it in the previous video. This equation describes the slope of some function y equals f of x at any point, x comma y. And so let's consider what's going on in this problem at the point negative 3 comma 3. Well, at that point, this differential equation states that my instantaneous rate of change would be negative my x coordinate divided by my y coordinate, or in this case, a positive 1. And note that that's a slope we should be pretty familiar with. It would look something like this, a slope of up 1 over 1. And so what that means is at that point, if I just draw in a segment like the one I just made, I would say that if my function goes through this point, for that one instant, it would look like what I've drawn, because the slope here is 1. Well, what about at negative 2 comma 3? There, my slope would be negative of negative 2 over 3, or 2/3. And consider a slope of 2/3 going to be less steep than a slope of 1, still positive. So maybe we could say it looks something like this. And what I'm going to do is complete this slope field for all the points that you see shown on the grid, as well as the points we can't quite see, the points on the axes that complete these rows and columns. And that's a lot of points. For a grid like this, it's 7 by 7, so we're looking at 49 points. But think of some ways that we can shorten this process. The slope will always equal 1 when the x and y values are opposite. So I would get a slope of 1 through all of these points here. Also, let's try to consider another easy slope to draw. That would be a slope of negative 1. And that could happen for a point like 3 comma 3, where if I look at my derivative value, I would add negative 3 over 3, or negative 1. And that's also a very handy slope, because anytime my slope is negative 1, I'm drawing that same perfectly diagonal segment, but in the downward direction. And for this particular problem, this is going to happen whenever y equals x. And notice how as I go through, I'm marking the slope values right by the point, just as a reference for myself, and then drawing in the slopes at all those points. And what I'd like you to do are think of some other useful slopes, ones that are very easy to draw. Perhaps something like a slope of 0, which we know would be perfectly horizontal, or an undefined slope where we know we would have a perfectly vertical slope. Well, in this problem, considering my differential equation, my slope is always going to be 0 whenever x equals 0. Similarly, my slope will be undefined whenever I divide by 0 or when the y value is 0. And the last thing to consider on slope fields is a situation where we might have a 0 over 0. We can't do it. That's an indeterminate form. We can't tell if it should be 0 or undefined, so we would leave that coordinate blank. In this case, that exact coordinate would be the origin. We're not going to have anything there. And so what I'm going to do Just through some quick mental math and by speeding up the video, I'm going to go ahead and complete the rest of this slope field. And now if you need to take a minute to make sure that you understand exactly how I got all these slope values for each of the points on the grid, make sure you do so before moving on. But I want you to note that this one was very quick for me to do because I noticed early on that the slopes were symmetric about the y-axis. I noticed that on the first row I filled in that I saw a mirror image with my slope values. Similarly, the slope values were symmetric in relation to the x-axis as well. So looking for the key slope values, 1, -1, 0, and undefined, and I just missed an e over here when I wrote undefined. But if you notice those key values and you notice patterns in the slopes, it makes generating a slope field a relatively simple and quick process. And now we'll get to what was the whole point of this. I mentioned at the beginning, a slope field is a visual representation of a function based on its derivative. And if you look, noticing how these slopes are changing as the x and y values change, you get a general picture of a function that follows those kinds of slopes. If I start from a point like this one, I imagine if I was going left, well, the next slope would tell me to start curving downward, and these little slope lines would direct me to make a picture like this. Moving out a bit, the slope lines tell me to follow the same type of path, just moving around a little bit wider. And hopefully you get the idea that this slope field is actually a representation of a common shape that we all know. This is actually the differential equation to describe a circle. And now you've seen two different skills that can be applied to this idea of differential equations, solving them and generating slope fields. There's going to be one more video in this series, and that's going to involve solving a particular type of differential equation just so you're exposed to it before you see it in practice. So please move on to that one and finish up your study of differential equations, and thank you for watching.